In the previous video, we introduced our angular quantities that we'll be using when we're working with angular kinematics. And in this video, I want to just very explicitly highlight those parallels between our translational kinematics that we used earlier in the semester and what we're introducing now. So I want you to really see we're doing the same thing. We're looking at things sort of from that same perspective when we're dealing with things moving rotationally or spinning that we were doing earlier on. We're just having it look a little bit different. So if we look on the left side of this handout, we have linear quantities. On the right side, we'll have our angular quantities. And at the top here, we're just defining all of our variables. So if we're thinking about our linear motion, our position, we can describe with that r vector. We also just used x, y, and you could use z. If we're thinking about velocity, that's v. If we put that into straight line motion, of course, we had our vx, vy, we could have vz. And then acceleration is a, ax, ay. And if we had anything in the z direction, we would label that as a sub z. In the angular quantities, we're now using theta for our position. Our velocity is omega, and I need to write that as an omega, not a theta. So omega is this symbol, and then our acceleration is alpha. We can also have, just like we do for the linear quantities that we went through, we can specify that we're going to use omega, and I'll do omega x, omega y, and omega z. The one that we're going to focus on this semester, just like for velocity, we primarily did vx and vy. We're going to do omega sub z. Remember that z is the axis, axis of rotation. We could do the same for theta. We could have how is my angle theta changing with respect to that x-axis, or we can rotate that plane, right? What is theta in the xy plane? What is theta in the yz plane or the zx plane? We are going to be focusing on theta in the xy plane. And then omega and alpha will be rotating then about an axis along the z direction. So omega is our vector for angular velocity. Alpha is our vector for angular acceleration. Again, we could have alpha z or alpha x, y, and z. We're going to focus on alpha z with our motion being in the primarily in the xy plane, alpha sub z. Okay, the next line here says when v and a are in the same direction, what do we know about the motion? So if our velocity and acceleration are in the same direction, then we know that we are speeding up, right, in that same direction. If v and a are opposite directions, so a is positive, b is negative direction, that means we're slowing down. The same is going to be true for angular quantities. So if we have omega and alpha in the same direction, we're speeding up. And so I'm just going to put that in the context of something spinning or moving in that angular type of way. So we wouldn't say spinning. I'm going to say it's spinning faster if omega and alpha are same direction. And if omega and alpha are opposite directions, it's going to spin slower. So that speed is going to change. And when we're thinking about angular motion, you want to think about that speed as how fast or slow something is spinning. When we did our kinematics early in the semester, we had these three constant acceleration equations that we used all the time and are continuing to use. We have them written here for the x direction. We've also used them in the y direction. Of course, when we did projectile motion or did free fall motion, we could write them also in the z direction if we had motion along the z direction. So these are our three constant accelerations equations we've been using. We're going to use equations that look nearly identical. All we're going to do is wherever I have a position variable, we're going to plug in theta. Wherever I have a velocity variable, I'm going to plug in omega. And wherever I have an acceleration variable, I'm going to plug in alpha. So this first one just becomes theta is theta naught plus omega naught. And I'm going to put this in the z direction for us, t plus my 1/2 alpha t squared. So the equations should feel so familiar because they're the same basic setups plus alpha t, and then our last one, omega z squared, is omega z naught squared plus our 2 alpha theta minus theta initial. So these equations are on your equation sheet. I think they're partway down that front page. Again, but they should feel very familiar because you hopefully know them or mostly have those memorized that we can use at this point in the semester. So we're going to use these equations anytime we know we have angular motion where something is moving with a constant acceleration, speeding up at a constant rate, slowing down at a constant rate. All of those scenarios would apply to these equations. When we did our translational motion, we have this diagram that we have, excuse me, talked about and used over and over and over again. We have our intervals, so we have our starting point, ending point, and then we have our 6 variables: starting position, ending position, starting velocity, ending velocity, acceleration, and time, and our positive direction. We need a similar type of diagram, so constant acceleration, if we're dealing with angular motion, is still going to have an interval. We're going to know what our system looks like at one point, and then what does it look like at another point. The diagram is a little more difficult, I think, to visualize because we're not translating, right? I don't have, with rotational motion, something changing position. It's just changing how it's moving. So the way I do an interval diagram for this angular motion or rotational motion is to do just a starting point and an ending point. And again, it's not really translating from one point to the other, but I'm just going to describe everything at this point in time. So at this first position, I would say theta naught and omega z naught. So at this first position, I'll just call this 0. At time 0, we have a position, a theta, a starting theta, and we have a starting instantaneous angular velocity. Then at some other point later down the line, at point 2, the end of my interval, we have a new theta, which is going to describe how many rotations our object or our system have gone through. And then we would have some final angular velocity, omega z. And then from that, across that interval, from here to here, we would have an acceleration, so a sub z, and there would be some time. So we still have those same 6 variables. Again, the picture is a little bit different because the fan or the blades, whatever I'm showing here, are not physically moving from somewhere to somewhere else, but the whole thing is spinning. So when we're looking at this, sometimes it's also useful to put in a direction. So maybe here I could just put in my picture, initially we're spinning this way. And so I can see that direction of motion. It helps to sort of visualize that this is angular motion as opposed to translational motion. We also need a positive direction. I mentioned in the last video that we could think about that positive direction as either clockwise or counterclockwise. So somewhere in your picture, you need either something like I just drew there, showing clockwise motion as positive, or the other way, showing counterclockwise motion as positive. So the diagram is going to be the same. You need a starting point, ending point. You need all 6 variables, 2 for position, 2 for velocity and acceleration and a time, and then also your positive direction. So the general approach as we work through problems here is the same as a constant acceleration problem that we did earlier in the semester. So we're reading the problem, recognizing its constant acceleration. First thing we should do is our diagram, right? Set up the diagram, put in all the information that you know, and then we jump to one of our starting equations. Once you've got your starting equations, rearrange, solve for the variable interested in, and then you're doing the math. So hopefully this page is kind of like a little cheat sheet, sort of showing the relationship between the 2 different types of constant acceleration motion that we're looking at, the translational that we've already worked with, and now the new angular motion that we are introducing in the second part of chapter 4.